Hi, everyone. Thanks, everyone, for coming out today to our ECOM seminar. So I am really, I would say, extremely happy to have Theodore Koenig today. I met Ted a few years ago while I was doing my PhD, and he was working in the same group, like 5 years ago or something like that. And I went to his thesis defense like last year, at the end of last year, and it was amazing. So I went like, oh, he should come give a seminar here. So Ted, as I say, got his PhD at the end of 2018, and his work was about aircraft measurements of bromine and iodine from the sea surface to the lower stratosphere. Ted got his undergrad from Caltech in 2008 in chemistry with minors in history and geological and planetary sciences. Ted's work has been focused on max Doas retrievals of trace gases in remote environments. He has particularly focused on VRO and IO and constraining box models to infer total inorganic bromine and iodine. These measurements have been of use to the satellite and global chemical modeling communities. So I believe in the future he will be working as a postdoc in China, or that's the plan. So he will be in China for a few years, I guess. With that, thanks, Ted, for coming out today.
All right, okay. Thanks for the introduction, Ivan. So I'll be presenting today on the iodine work that's formed part of my thesis. This work is still kind of in the process of getting published. Part of the talk is in review right now, probably going to be published soon, and the other part is kind of getting close to submission. Started off with the picture here of the contrast team. This is kind of a central part of the work I'm going to be showing here. So with that, I think I'll jump right in. So this is kind of an overview of what iodine does in the atmosphere. So without getting into too much of the detail, here we have sea salt aerosol and other emissions from the ocean surface. And in some contrast to chlorine and bromine, we actually have quite a large source of inorganic iodine from the ocean surface. So large, in fact, that if we integrate the total source, it dominates over the organic source. On top of that, the organics have a lifetime that's no longer than about 7 days for methyl iodide. So as a result, almost all of the iodine is going to be quite rapidly processed into inorganic iodine in the atmosphere. And then what we do is we measure IO. Sorry, this is looking slightly different than I expect. Okay. So we measure IO down here. That's right. Okay. And we can then use chemical modeling of the different photolyses and the partitioning to understand the total IY budget. And some of the effects of this is that in the troposphere, it leads to a significant loss of ozone. About 9% of the total tropospheric ozone loss is due to IY. And this in turn can lead to irradiative forcing. But up here in the stratosphere, we've always had to contend with the fact that we have only upper limits historically for inorganic iodine and very small injections of methyl iodide into the stratosphere, reflecting the fact that it has about a 7-day lifetime. So the impact in the stratosphere has been a kind of source of great uncertainty in the stratospheric ozone budget. But one thing to keep in mind is that a side effect of all of this rapid photolysis is that on the per atom basis, iodine is very effective at destroying ozone. Another aspect of iodine I'm going to be talking about here is the heterogeneous chemistry of it. So that inorganic ocean source follows essentially this basic scheme. So ozone gets adsorbed into the surface, it reacts with iodide, oxidizes it to HOI, and then the HOI can be emitted due to its vapor pressure. You can also have the HOI react with iodide, and that will produce I2, which can also be emitted. So the essential mechanism for this release from the ocean surface is that it's ozone driven. You get ozone, it impacts the ocean surface and stimulates iodine emissions. The thermodynamically stable form of iodine is ultimately iodate. If we had kind of no driven atmospheric chemistry, no driven chemistry whatsoever, we'd expect iodine over time to integrate into iodate ultimately. And if you go into the deep ocean, this is the overwhelmingly dominant species of iodine. This is kind of a look at this process in terms of what happens on aerosol. And this has been demonstrated to occur on sea salt aerosol. And one thing worth noting here is that these are kind of theoretical steps for everything past the first oxidation. We know that if we expose iodide aerosol for long enough, we get to iodate, but we don't have a kind of thorough understanding of the kinetics. We do know that the first step of this reaction is approximately 1 million times faster than the reaction with bromide, and the result is that uptake of ozone onto sea salt aerosol is believed to be dominated by trace amounts of iodine in the aerosol, that they dominate over any reaction with chlorine or bromine. So let's look at a kind of WMO perspective of iodine in the LS. So overall, we have this low upper limit, 0.1 ppt roughly, of measurements of iodine oxide, and this is based on measurements from twilight on a number of different platforms. So we have Boots and Bush and Punt all used balloon measurements, track the sun, and just look at the absorption around twilight. Venberg et al. In 1997 used ground-based measurements primarily from Arizona and used an FTIR and got to a similar upper limit, roughly speaking. Methyl iodide, we have actually some detections. The global average comes out to about 0.04, 0.05 ppt, which is not a huge number. And then for particulate iodine, there's been actually repeated qualitative detections of a large kind of increase in the iodide, in the frequency of iodide observation, I should say, around the tropopause from the Palms data from the NOAA group right down the road from us. But they haven't gotten a quantitative detection of the iodine. And just showing here that you can see the iodide peak kind of course will have a tendency to correlate with bromine, and it'll also have a tendency to correlate with mercury content around in aerosols around the tropopause. So this brings us to the WMO 2018 estimate. And going into WMO 2014, the last time iodine was examined thoroughly was roughly in the 2006. So they just kind of take the upper limits for the total here, say that's 0.1, that's 0.05, and you get about 0.15 ppt total IY in the stratosphere. It's, like I said, much more efficient than chlorine or bromine at destroying ozone, however. So you can look at here, for the ozone destruction potential of 1 atom of chlorine, iodine will destroy about 600 molecules of ozone per atom compared to that. So even at these small concentrations, if you're looking at what's in the lower stratosphere, this looks potentially competitive with that, going kind of ignoring all of the dynamics and stuff like this for now. Based on measurements we took during the Terreiro campaign that were in Fulcamaral and Saez Lopez et al. 2015, we found that what we see in the TTL would be more consistent with a roughly 0.7 or 0.8 ppt injection of IY. So if we propagate that, then we would say that iodine is by far the dominant ozone-destroying halogen in the lower stratosphere. So there's something of a hole here that we need to close. How could all of these lower limits in the stratosphere be compatible with the amount of iodine we're seeing right below the tropopause? So this is from the Terreiro campaign. We had quite a suite of instruments. I won't spend too long here, except to highlight that out of this Terreiro and contrast work, we've published these papers on halogens, with the green ones roughly in the troposphere and the red ones in the stratosphere. How do we do that? We use the telescope here, and I'm not going to dwell very long on the technical aspect here, but we measure a slant column of photons that we collect primarily in a limb geometry, And then we can constrain the aerosol in order to understand how long our path length is, what the concentrations of IO and BRO we are measuring are. And that allows us to do things like this. I think C1 might be here. So this is from C1's 2015 paper. And what we can do is we can look at IO signals as a function of altitude. And this is showing our detections along a number of flights. And then this was further digested into the following kind of average IO profile we have from the surface to the stratosphere. And what you can see here, I would say roughly speaking, is that we come from kind of an enhanced level at the surface. Then there's the high variability, which I'll come back to later, in kind of just above the surface. And then we get into a kind of tropospheric background level with a kind of remarkably consistent 0.1, 0.2 ppt IO concentration. And this is kind of another look at the same data where I just show latitude against altitude, and then I color code it by the amount of iodine we observe. And whoops, you can see that that high variability there is driven by a feature right here that I'm going to come back to later. But then we have this kind of quite consistent, low but non-zero amounts of IO through the whole troposphere. So let's kind of look at how we might be seeing things a little bit differently than those twilight measurements. So here I've got the total amount of iodine in the gas phase and how much of it, based on a chemical box model, I expect to be existing as each species as a function of the time of day. And for here, I'm looking at conditions in the upper troposphere. So for the upper troposphere, the expectation is that IO should peak around the twilight hours. And then if we'd have a daytime measurement, then I'm only able to measure about 10% of the total IY, and I'll have less leverage than the measurements at twilight. If I go to the lower stratospheric conditions, then if I take a daytime measurement, I have access to about 60% of total IY as IO, which I can measure. And then the twilight measurements are highly dependent on the specific time that they're taking their measurement, but it's going to come rapidly down from 60% to, let's say, about 20% at sunrise, maybe 20 to 30% at sundown. So we have some hope of potentially having a better detection here in the lower stratosphere, just because of the time of day we're going to be measuring at. We're going to be measuring at the middle of the day. All the previous measurements were twilight measurements. We got roughly a factor of 50% more sensitivity in the stratosphere. So this is a paper from the Saez-Lopez, 2015, which is where we got this number of a large injection of IY into the stratosphere based on our tropospheric measurements. So these are all the tropospheric measurements we were using at the time, and they essentially line up with two different cases here. A case where we allow iodine to recycle on ice surfaces, and a case where we say, okay, iodine is actually going to be lost to the ice surface, and the result is that as we go up in the troposphere, we're going to have a slow loss process. And roughly speaking, it's ambiguous which of these two cases is true here, but then if we go to the IY, you can see that the prediction that's consistent with this is well above this WMO limit. And if I put on a few more numbers here, this is what approximately Venberg would get as their upper limit for IO. They would say that the troposphere is below this. Granted, that's very much true. And then they would say that the IO up here is below this line, which if we extend the consistency here is below both of our predictions based on what we see in the upper troposphere. And I can add another number here, which is the Boots, which is the most recent balloon profile, and they give us a slightly lower upper limit in the lower stratosphere. So the result here is that there's no previous detection. All we have are these low upper limits, which appear to be incompatible with the upper tropospheric measurements we have. So this brings us to the convective transport of active species in the tropics, CONTRAST, which was another mission we flew on the G5 back in 2014, January and February. We are based out of Guam, and I'm going to focus on two flights here because they are the ones relevant to the stratosphere. On RF6, we flew north. We got close to the jet, which is approximately the same location as it was a month later. And then we flew back to Guam. We went up at one altitude, climbed a bit, and then came back at a slightly higher altitude. For RF15, we actually successfully crossed the subtropical jet into the stratosphere. At the northernmost point, we were well into the overworld, climbed, turned around, and came back down on the same path for the most part. And from a kind of chemical tracer perspective, and dynamical tracer perspective, this is what we were seeing. So here on the time, I've kind of erased the time axis just to give a conceptual idea of what we're doing here. This is the horizontal wind. So you can see we come up to the jet, and then we go into the stratospheric side, and we get to the lower winds of the stratosphere. At the same time, you can see potential temperature climbs up to overworld values after we do the climb at the northernmost point. And you can see that water comes down from tropospheric values to very low stratospheric values, and ozone correspondingly goes up and then climbs very high when we cross the jet right here, and we have these 3 high ozone features. And this is the IO we measure during that same time period. So in the gray here are individual 30-second measurements, and then in black I'm showing our 5-minute averaged retrieval. So just to make it clear, what I'm doing here is I'm actually averaging all of the spectra for those 5 minutes and then reanalyzing the data. And you can see that the IO is going up roughly in line with ozone here, right? So that's just kind of a partitioning effect, roughly what we'd expect. As we increase ozone, more of our iodine exists as IO rather than I atom. But rather than continuing to follow the ozone up, what we see is that the iodine falls down, and it never quite gets to 0. You've got a few low points here, but we keep seeing this iodine persist through the stratosphere, but it's not following the ozone concentration. It's not partitioning as though we were conserving our total iodine budget. So this presented something of a kind of mystery to us. Where is the iodine going? And if we actually try and go through all of the partitioning, so here in the bottom panel, I've kind of simplified the partitioning into the 3 major species. You can see everything else is essentially these little tiny bars up here. They're just trace species. Most of it is IO, HOI, based on our current knowledge of the chemistry. And you'd expect iodine, if IOI was conserved, to follow some sort of line like this, where it comes up as we increase ozone, caps out, and comes back down. We don't see that. What we see is that the IY, or the total inorganic iodine, follows this trend. And then just kind of guide your eye, I show the water to ozone ratio on a log scale behind this. And this actually seems to line up kind of remarkably well. So we took this as the first indication of there's some sort of kinetic process going on that's following the water ozone ratio. So we've had those results for a few years, didn't know how to kind of fully digest and publish them. And then the ATOM campaign happened. So ATOM was 4 circuits in 4 different seasons, kind of around down the Pacific, up the Atlantic. And what I'll be showing here is ATOM 2 data, and ATOM 1 and ATOM 2 data, because after they detected some halogens, we did calibrations with them, with Jose Jimenez's group at CU Boulder after the fact, to try and get quantitative measurements of bromine and iodine. So giving you an overview here, I'm going to be, from this point in the talk on, roughly speaking, looking at data in kind of a very simplified classification way. Just trying to be able to connect things between, to account for the fact that we don't have these instruments on the same aircraft, they're not at the same campaign. I just want some kind of universal comparable axis. So I'm going to use that water to ozone ratio, and the red points here, I'm going to call those upper tropospheric, blue points lower stratospheric, and the yellow points are this intermediate regime. From a kind of dynamics perspective, we would probably give different definitions to each of these bins based on the latitude bin, but big picture wise, I'm just going to say lower stratosphere, upper troposphere, something in between. So you can see RF15 and RF6 here. We have coverage in RF6. We go from the troposphere into that intermediate regime, and then RF15, we get to the stratosphere. We have some coverage from the earlier Terreiro campaign. And then ATOM has coverage, particularly kind of in these extratropical regions, but has some sporadic coverage in the tropics as well. And this is what the IO looks like for kind of just two examples we have from RF15. So the black line here, I should emphasize, is just to guide your eye. It's actually not used in the analysis at all. It's just so that you can kind of understand better what the program is actually fitting into. It's kind of blind to this higher frequency noise. So in the troposphere, we've got kind of a nice, reasonably nice IO fit. You can see there's a lot of noise on it, but the overall signal comes out clearly. And then if we go up into the stratosphere, we've still got an IO detection at a very low concentration. And then I've got a picture of Pedro Campuzano-Yost here, who was kind of one of the leading people who flew the AMS. And I'll come back to this later, but we get three main ion signals from iodine in the stratus on the AMS. So the main signal here is the I+ ion. So you can see that we get an overall increase in signal as we go to the stratosphere, just by looking at the I+ ion signal. And then HI and I2+ here are, roughly speaking, this is an indicator for iodide, and I2+ is an indicator for iodate. And what we see is that in the troposphere, we have quite a bit of iodide, almost no detectable iodate in this particular instance. And then we move to the stratosphere, and our iodide signal has come down, and our iodate signal has come in clearly. So we're seeing a change in the chemical partitioning in the particles, and overall, an increase in the iodine content of the particles. So these are the kind of calibrations I was talking about earlier. We did calibrations for all of the halogens, but I'll focus here. The main thing is that the halides follow a nice line on this HX+ versus X+ metric, which gives us more confidence in our individual iodide calibration. So you can see it just comes down kind of this one-to-one line, and as you go to larger halogens, you get less HX+ signal. And then the oxidized halogens, perchlorate, chlorate, bromate, iodate, follow a similar line. The the extra ion that this extra signal is going into is different for each of these species, but in the case of iodate, it almost all goes into I2+. So we have some small IXOY signals, but most of it goes into I2+. And then here, these are, if I kind of group all of my data from ATOM 1 and ATOM 2, where the different ion ratios line up. And you can see that this is actually an ATOM 1 point in the stratosphere, looks a little bit odd, but for the most part, all of our bin data falls along this kind of partitioning line between iodide and iodate, which gives us more confidence that the overall partitioning, we're actually seeing that. If I look at IY gas here, and I use the same metric here of water versus ozone, I can get that for all the extratropical data, it falls quite nicely on what here is a single exponential fit. So what I'm going to do going forward from here is I'm going to say, okay, so my IY, if I want to predict what it is going to follow this same exponential fit, and I've got my bins here looking at it the same way in terms of kind of 25th, 75th, 10th, and 90th percentiles. And if I assume that all of this gaseous IY that disappears becomes particulate iodine, just kind of taking the fact that it's increasing in the particles, decreasing the gas, then I can try and take a larger picture of what chemistry might be happening and try to connect these two campaigns. So these altitude bins here are just kind of from a zonal climatology, mapping that ozone water axis into altitude space at mid-latitudes. And as my IY gas goes down from the troposphere to the stratosphere, I'm going to increase my IY part by the same fit. I'm just going to assume the IY is overall conserved. If I do that, I can also take into account the fact that I'm not showing super clearly here, but there's indications that iodide is roughly conserved through the whole system. The absolute amount of iodide in the aerosol is roughly constant. I can get an amount of the IY part that exists as iodide. Because my volume of aerosol changes, this still leads to a small change. And here I get to something which is rather new, which is, like I said, we know in sea salt aerosol, iodide reacts with ozone very efficiently. So we just ask the question here, what if the same thing happens in sulfate aerosol? And if we do that, we get a very significant gamma here, actually. It's on the order of about 10 to the minus 6, maybe 10 to the minus 5. And the prediction then is that this should actually be potentially a very important ozone loss process, that the iodide that remains in these sulfate particles can react with ozone through heterogeneous or multiphase chemistry and deplete ozone. So with that kind of hanging around, I'm just going to kind of dive back in here to show how we're going to get this budget working. So the lines here are showing the modeling roughly as we had it in Saez-Lopez 2015, just an ice recycling case and non-ice recycling case. And if I show here, this is the Terreiro IO averaged over all of the data I have in that upper tropospheric bin, and I can convert that into IY. And I can do the same thing for contrast, and at first blush, it looks like there's a contradiction here. And that's actually because in contrast, just through kind of coincidence, we sampled very low ozone air when we were at high altitude. This is partly because we were over the Western Pacific. But if I match the ozone to the zonal climatology, what I get is that this value here should move back up. And that's somewhat clear over here. If I just look at the IY partitioning, you can see I'm closer to that point over there. So we think that this lends credence to the idea that iodine is recycling on the ice surfaces from the tropospheric data we have. As I go up through the intermediate bin, though, I'm starting to fall clearly off of this line. In fact, I'm getting into what looks like iodine's not recycling on ice at all. And if I go still higher to the stratospheric data we have, it actually looks completely incompatible with how we would understand the iodine chemistry without something else going on. It looks like the iodine here and here can't be following what we have in the model. So what we do is we impose that same exponential fit function that I showed on the previous slide, and we say, okay, so in the troposphere, where ozone is low and water is high, it's essentially following the process we understand. But then I'm going to create this parameterization, and it's going to say that all of this iodine that's disappearing is going to appear as particulate iodine. And if I plot the atom points, it starts to look like, okay, maybe this is working. It's actually increasing. And I can show the fit, and you can see that there might be some iodine loss. These are all below the fit line I get here. But the overall trend remains essentially compatible, that it actually looks like the iodine is moving into the particles. So then we start to look at ozone loss. What does this mean in terms of ozone? So this is done with the CamChem model. And here is the same panel from the last graph. And then I'm looking at, this is the percent of the total odd oxygen destruction, where we count every odd oxygen that's created or destroyed. And I'm showing here only the contributions from the halogens. So the big thing down here is that iodine is very important in the UT. So that 9% effect it has in the troposphere, we're still seeing that. And that's basically a reflection of the fact that we haven't really changed anything from the literature there. As we go up, the contribution of the gas phase iodine fades, much as the gas phase iodine itself fades. But the gamma for ozone uptake I've put in for the particles comes in and actually is quite a significant ozone loss process here in the lower stratosphere. If I extended this farther up to about 30 kilometers, both of them fade to essentially zero, maybe even at 25. But here in the lower stratosphere, the contribution from this heterogeneous process is actually quite significant. So this is kind of switching gears quite a bit to look at part of the reason why we should probably care about this right now a bit more. So what I'm showing here is several recently published results of iodine deposition. And we have two sets of measurements which look at a glacier in Greenland and one at a glacier in the French Alps. Then we have a very recent set of paper by Zhao et al., where they're looking at spruce trees in the Qinghai Tibet Plateau. And from the longest record, you can see that over Greenland, okay, you might see some sort of trend mildly upward here, goes down, comes back up. Nothing super jumping out here. It looks overall quite compatible with the Alpine Glacier. But then if we get here, we see this kind of sudden departure of all of the time traces since circa 1950. They all trend upward. One exception you might notice already is that the green point's not doing that. I'll come back to that later. But if we zoom in, you can see that right here around 1950, we begin to see this departure. And Greenland doesn't look quite as impressive overall, but you can see in terms of the magnitude, it's still going up. And the other thing you might notice here is that these two axes are quite different. Part of what is driving that is that organisms in general, iodine is an important micronutrient, so it has a tendency to focus in biological materials. So part of what's going on is probably that the spruce are enriching themselves in iodine by a factor of roughly 1,000 compared to the glaciers. This is not unprecedented in observations we have from the past. But if I go a little bit further, you can see that this point down here isn't doing anything. There's actually another unpublished result that we're aware of, at least one, where another alpine glacier shows no significant trend. So I would say that there's kind of indications of some sort of major departure in 1950, but we will want to get more data before we read too far into this. For the Greenland data, there's been some more analysis of that. So I'm blowing it up by a factor of 4 here. And one thing you can see is that the Greenland data correlates actually quite nicely with this one spruce time trace. The R is about 0.77. And Cuevas et al. Have broken this trend into 2 parts. So from 1950 to 1990, this correlates quite nicely with the ozone-induced increase in emissions of inorganic iodine from the sea surface. Whereas after 1990, this instead correlates with increased biological activity. And in the case of the Greenland, it's specifically a reduction in sea ice, which is allowing for a longer growth season for microalgae. So this is essentially to say that there are probably multiple feedback processes going on here, but there appears to be an increase in iodine tied to both this ozone-induced increase in inorganic emissions and then a possible kind of biological feedback leading to increased organic emissions. And the reason this probably matters for the stratosphere is that if we look at this propagation of sources, so here we run the CamChem model where we turn on selectively only organic iodine and then also only the inorganic iodine. We can see that we propagate that the inorganic iodine dominates at the surface, but then has a fading dominance as we go to higher altitude, and this essentially reflects washout. The HOI is the kind of dominant species, and it's somewhat soluble, so we'll eventually have wet deposition removed from the atmosphere, and we don't completely remove it, but we reduce its importance relative to organic iodine. But in any case, both of these appear to be increasing, so the result is that this could lead to a ozone depletion effect. And if we say this has been operating over the last 70 years, it's about 70% of the iodine could be new since 1950, then we would get an effect of about 1 to 2 Dobson units in the lower stratosphere over that 70-year time span, which is potentially compatible with kind of 0.6 DU trends we see since 1985, where we can't explain those using halons and CFCs, HCFCs, etc. So to summarize this part of the talk, we have the first IO detection in the daytime lower stratosphere, and we find that there's about 0.11 ppt IY gas, a result of about 0.06 ppt VIO. From ATOM 1 and ATOM 2, we have the first quantification of aerosol iodine in the LS, and we find that, again, iodide is a decreasing fraction, but it doesn't go entirely away. And from a mechanistic perspective, the persistence of iodide in IO means that we should have some sort of active iodine chemistry that's preserving the iodine over kind of 10-year time spans based on the age of the air we see in the LS. And then our measurements support a 0.77 plus minus 0.1 pptv IY injection. This is consistent with the high end of the estimates from our earlier work. And then if we look at the ozone loss processes in the lower stratosphere, we can see, if I look at the halogens only over here, that we find chlorine is responsible for about 28%, bromine is dominant at 40%, and then iodine is in fact comparable, slightly larger than chlorine, with this heterogeneous process we hypothesize being the largest contributor in terms of what iodine is doing with ozone. And then in light of the kind of fact that we have this increasing rate of deposition of iodine, we think that we need more measurements to look at whether there's actually a trend, and this is responsible for part of the unexplained ozone depletion we continue to see. So switching gears somewhat here, I'm bringing back this graph where I noted that there was a lot of IO in this one chunk of this graph right here. And what's going on there? So this happens to be mostly takeoffs and landings around Antofagasta, Chile. There's a few other things going on there, but that's most of what we're seeing. And I'm going to break down kind of one profile here. So I identify layers A, B, and C, which I've shaded here. And you can see that they're decoupled from the boundary layer. I just put the boundary layer top here based on the water and the potential temperature. And then inside each layer, they're kind of roughly a constant lapse rate. I'm going to say that they're well-mixed layers. And the other thing you can see is I have the UHSAS and the CDP, just pure particle counts here, not looking at anything else more complicated yet. And you can see that the coarse mode particles peak slightly in each of these layers. There might even be another layer up here hiding. And the other thing you can see is if I just kind of linearly interpolated the ozone, each of these layers is depleted somewhat in ozone. And in this case, we actually get down to below 10 ppb ozone. That's pretty low. So we must be doing something to get rid of all that ozone. So what I show here is that if I just take the aerosol surface area, assuming all of these particles were spherical, then I get this yellow trace here, and my IO that we measured lines up reasonably nicely with that. So it looks like there's some sort of correlation between these particles and iodine. So what are these particles? Looking at each of those layers again, A, B, C, you can see that there's a pretty well-defined, especially in the lowest layer, kind of accumulation mode and coarse mode for the aerosol. They look pretty nice. And then we have HSRL data. So up here in the HSRL data, I can show that we see cirrus clouds. And down here, we've got kind of this stratocumulus layer. And you can start to see this layer here and these layers here. And I've got color-coded along the flight track the IO mixing ratio. And you can see that when we go into this layer, we see IO, and when we go in this layer, we see IO. It's cut off back here because we can't turn on the HSRL right at takeoff. So you can see that these layers then persist, and those are layers A and B kind of mixed in together there, and that's layer C down there. And then if we look at the depolarization data down here, this is a stratocumulus cloud consisting of ice and water. I guess going through this rather simplistically, these blue colors here are roughly consistent with spherical particles, kind of constant depolarization, very little depolarization. If we go to higher depolarizations, we're seeing non-spherical particles. So those cirrus clouds up there, they're ice crystals. We get significant depolarization. And then you can see these layers, especially this lowest one, appears non-spherical particles. And then this one up here might be non-spherical, but then it kind of fades into more spherical particles. So we hypothesize that this is dust. And then as we get closer, kind of farther from the coast, we're slowly deliquescing that dust until it becomes essentially spherical. So we're just seeing water accumulate on that dust, and then we get kind of more like water droplets. So we end up besides kind of that dramatic example, we actually intercepted 27 events that meet kind of a certain criterion here of where both IO goes up, ozone goes down, and we see a large increase in aerosol surface area. So on here, I'm showing in blue the track of where we observe layers on the HSRL below us, where when we then intercept that same aerosol layer, we see such an enhancement. So you can see that this is South America here. We observe such layers actually for quite an extended period here. So this is thousands of kilometers north and south, hundreds of kilometers east and west off of the coast. And we also have WRF back trajectories for these layers. And then what I'm showing here is what I call a layer contribution. So I'm taking the boundary layer contribution from the back trajectory for every intercept and then weighting it based on how strong the boundary layer contribution was and then dividing it for all the layers. And we can see a few important source regions. We can see the Atacama Desert seems to be an important source region here. And then this is a smaller desert called the Sechura up here. And then you can also see this is the Altiplano. And then back here, this back trajectory, about half of it maps to that single point, which actually just seems to be a false positive detection, where our criteria weren't able to exclude that, but we can say it's an outlier from this trend. And then if I look at the Sechura data, it falls significantly lower, but it's still on the same trend line. So it appears that the IO mixing ratio we see correlates quite nicely with the aerosol volume, that there's a real connection between this dust we're observing and the iodine we're observing. And based on this, I went back and kind of searched through the literature, and there's this thesis out of the University of East Anglia by Yodel, and they had seen this correlation between non-sea salt calcium and iodate content of aerosol, which looks quite nice across 4 different ship campaigns. And they had hypothesized that what they were seeing was that the calcium was an indicator of basicity, and that they were just slowly titrating iodic acid out of the atmosphere. So that what's happening here is that the dust comes out with kind of calcium carbonate or some other base, and then it accumulates iodic acid as it's on its path through the atmosphere until they intercept it on the ship. Legrand et al., which was one of the glacier deposition papers, looked for such a correlation, and they find nothing. There's no correlation between calcium content, Sahara dust events, or anything like that with iodine. Their R squared ends up being 0.04. So we come up with this hypothesis instead, because we see this release of iodine, that the iodate has accumulated with the dust on a kind of geological timescale. It is being titrated, but in dry environments, the dust gets a small amount of iodate, and then when it's lofted, that iodate gets re-volatilized as a result of some sort of atmospheric processing, such that it's fully gone by the time we deposit to a glacier. So looking at that, I instead get the IY here instead of the IO. This is, roughly speaking, showing kind of the same overall trend. And I'm going to make a lot of assumptions to try and get some kind of meaningful number I can compare out of this. So the first is I'm assuming the dust has a density of 2.7 grams per cubic centimeter roughly. And if I do that, I can convert this slope here and say that the mass fraction of iodine is roughly 8 and 10 to the minus 4. If I do the same processing, kind of from a different perspective for the Yodel data, the Sahara dust would have a kind of 1 to 5, 10 to the minus 4 mass fraction. And in the grand scheme of things, considering we're measuring in very different places, I think this is reasonably consistent. So one thing to note here is that the calcium content of South American dusts is roughly 3 times less than the Sahara. So we would expect that if someone did a similar measurement scheme as Yodel off the coast of South America, their slope would be roughly 10 times as much, because we have ballpark kind of 2 to 3 times as much iodine, and then they the calcium we're going to be dividing by is about 3 times less. So this is hopefully something that can be tested in the future, but we're going to move forward with the hypothesis that there might be a missing source of iodine from all of this. So if we take the global dust emissions from Mahawal, this is just one recent paper, you can actually get whole number factors off of this, depending on which source you wish to cite, but I'm going to just take 2,500 teragrams per year, and I'm going to say that it has that Sahara ratio of iodine, roughly 1 to 5, 10 to the minus 4. This would be an iodine source of 250 to 1,250 gigagrams per year. That would be about 6 to 25% of the total iodine emissions globally. And we think that this is something that we're going to need to look at more carefully because it could suggest that there's a huge source of iodine we're missing at the moment. Currently, we're investigating the impact of the dust layers on ozone. Like I showed earlier, the ozone is definitely depleted in them. What I'm showing here is if I assume the ozone destruction persists for 4 days, and here I have the aerosol mass of the dust, then I can get kind of this relatively nice line. If I look at the back trajectories I have and look at the ozone destruction in them, and I assume this was the only process, then most of my back trajectories would suggest that they've had only 1 to 2 days of processing. The longest in processing we would find on any intercept is about 5 days. The lifetime of dust in the atmosphere is usually on the order of about 10 days. So it suggests that, if we were able to intercept these off the coast through specific targeting, we might find more ozone depletion. That would, if I kind of integrate that through this global budget again, this is a huge amount of extrapolation, I get ozone destruction effects on the order of about 0.1 to 1% total tropospheric ozone destruction. Again, this last part here is definitely a work in progress. We need to incorporate kind of other heterogeneous ox destruction mechanisms to check whether those might be contributing to or competitive with this iodine-based chemistry, which is quite fast but might not be the whole story. So wrapping up here to the kind of final conclusions, stratospheric inorganic IY has been measured for the first time. We find it's responsible for about roughly 1/3 of total ozone destruction from halogens in the lower stratosphere. There's a lot more we need to find out about why it behaves the way it does, what's going on to drive this partitioning toward iodate. We have indications that it's recycling back to iodide in the gas phase, but what's driving that? Desert dust could be a significant source of iodine to the atmosphere. We have this hypothesis that there should be a ubiquitous small amount of iodate present in almost all dry dust. More measurements are needed to actually check whether that's the case. And so we also need to investigate how big of an impact this has on tropospheric ozone. And then finally, this is all based on, for the stratospheric iodine, a handful of research flights, and same thing for the dust, it's 27 intercepts. We need a lot more data, essentially, to confirm and corroborate that this is really something that's going on globally. At the moment, I'm forced to extrapolate from a very small number of data. So a first step toward that is that since early 2017, we've operated 2 mountaintop sites, one at Maido Observatory on Reunion Island, another at Mauna Loa. And we've been getting data on Io and other species, which I guess at this point is a little over 2 years long. So we're going to be looking at that for hemispheric seasonal trends, trying to see if there's anything going on. And we have the Tiger campaign, which is currently in the proposal stage, planned for spring 2021. The plan here is that we're applying for 50 flight hours. We would fly from Broomfield to Kona, Hawaii, and then we have a payload which would measure both particulate iodine and gas phase iodine simultaneously. We're also targeting a specifically new particle formation, which might be tied to iodine. This is an aspect of our research that I haven't spent very much time on in this talk. But the plan would be to kind of conceptually reproduce the RF-15 and RF-6 from contrast flight plans. We would wait for the subtropical jet to come close to Hawaii and then fly north to intercept, get into the stratosphere, and return back. Similar to those last 2 points, and we would also be the first particulate measurements from the AMS we would get at the G5 altitude rather than the DC8. And with that, I would like to acknowledge this work was funded largely by NASA and NSF, specifically these three NSF grants. ATOM was a NASA mission, and I'd like to thank the Terreiro, Contrast, ATOM 1 and ATOM 2 science teams. That's probably dozens, if not hundreds of people who really made this work possible. And thank you for your attention.
Great, thanks, Ted. Are there any questions?
Hi, thanks. So, thank you. Ozone deposition measurements over the Sahara Desert show higher ozone uptake at the ground than kind of expected by our understanding of ozone uptake by the ground. And so would you expect that what you're seeing in the troposphere to be important for ozone removal?
So I would say I wasn't aware of that. I'm actually surprised how little we know about iodine in the Sahara. The fact that the hypothesis here is that it exists as iodate, which is relatively insoluble. You could expect that might, if you have very low rain levels, you might accumulate iodate just because you don't have enough water to remobilize it deeper into the ground. The trouble is that the iodate itself does not react with ozone. That said, we do know from the stratosphere, based on the fact that in 10-year aged air, we still see iodide. There must be some recycling process. So I guess the quick answer is probably that it might be connected, but if it is, there's going to be a lot more chemistry going on. You'd need something to mobilize the ions to allow that chemistry to happen.
I know Johan has some questions.
Thank you very much. Very interesting work. I have one question and one suggestion. Suggestion first, I think the ATOM, they have the single particle-based measurements. If you hypothesize that dust contains iodide, then that instrument might be able to provide some insight. They seem to be able to cover the correct size range. And I wonder, have you checked that? And
yeah, I will say the PALMS data, which is the single particle measurements I'm aware of, are not publicly available, and I'm not part of the ATOM team. But we have had some discussions with them. But that we're kind of decoupling that from the stratospheric work as far as for the moment.
Another question is, in one slide you showed the long-term trend of iodide from ice cores and stuff.
Yeah.
And then,
oops. Here?
yeah, and you mentioned that later another phase or another trend is driven by the change in like biogeochemical activities. Yeah, I was wondering if that's the case, I would expect some sort of seasonal variation. Do you see that in this data set at all? So
for the Greenland data where they see this ice effect, part of the problem there is that they're in the Arctic, right? So we've got basically sun on, sun off. So their seasons are a little bit different than elsewhere. The Legrand data shows, that's the kind of red and blue points here. You can see that as we go forward in time, the red points are almost always above the blue points. They find that almost all of the increase is in the summer only. That there's a very mild effect in the winter increase in emissions. This might also, right, this is biological activity based on sea ice thickness primarily. So it might be a local effect around Greenland, which I'm not sure if we can extrapolate that globally. I mean, yes, if we have more emissions around Greenland, that will contribute to a global effect, but it doesn't mean that the magnitude of this biological feedback necessarily fully translates. I mean, really, right, we're working off of 4 data sets, and there's at least 2 we know of that don't show this trend. We might not want to grasp too hard for straws, I guess, is what I'm getting at here. We don't want to overinterpret the data too far.
Yeah, following on from that, do you have any insight into why there's a significant difference between the PC1 and the PC2 data sets on this slide?
So The area where they are getting these trees, so they're spruce off of the Qinghai Tibet Plateau, and it's not allowed to do logging, so they can only use fallen trees. There's some discussion in the paper about the fact that PC1 is relatively close to the edge of the forest and has less shielding by the rest of the forest canopy, whereas PC2 was located in the heart of the forest, so maybe the iodine flux to it was different just because all the trees around it uptook the iodine first. There's also some discussion in the paper about the fact that you might not see it perfectly here, but there's occasional times where the PC2 time series becomes a little bit more sparse. There's some ring counting issues for it, but because there's no trend at all, that shouldn't help us very much. I would say overall, it's just complicated. There must be something else going on that we're completely unaware of, because otherwise, why should we see, like I said, there's another alpine time series that shows absolutely nothing. That indicates to me at least that there's something we're not understanding about the chemistry.
Any more questions? No? If not, let's thank again Ted.